Hello everyone, I am Fadel, and today I will be telling you how we can localize multiple people in the environment by relying on reflections of their bodies. This is joint work with my colleague Zach and my advisor Dina. Localizing people from reflections is a new area in wireless research. And the basic premise is that we can localize people without requiring them to hold or wear any device. So, in order to explain how these systems work, let me play a video for you that shows them in practice. These systems install a device in the environment, and the device sends out low-power wireless signals and measures how they reflect off different objects, even if these objects are in adjacent room. Now, if a person walks nearby, they can track his motion and map him in 3D space. So for example, over here, the red dot corresponds to the person's location. And these systems enable many exciting new applications. For example, they can transform your apartment into a smart home by tracking your movement and learning your habits. They can detect when you wake up and get out of bed, turn on the hot water, and turn on the coffee machine. And when you sit in front of your TV, they detect your presence and tune to your favorite TV channel. But when you lie down to sleep, they will turn off the TV. And also by tracking the inhabitants of an apartment, they can know where they are and adjust the lighting and heating to save energy. In fact, they can even be used to extend gaming consoles like the Xbox Kinect to track us even if we are behind the wall or in a completely different room. Now, past work has made major leaps toward this vision. But these systems still have two main limitations. The first limitation is that they cannot accurately localize multiple people at the same time. And the second limitation is that they cannot localize a static user. So they need the user to move. However, in the applications that I talked about, many times in a smart home, you might have multiple people, or the person might be static or might be moving at different times of the day. So in order for these systems to deliver their full potential, they need to be able to overcome both of these limitations. And this is exactly what I will be telling you about in this talk. I will be showing you how we can track multiple people at the same time, and I will be telling you how we can localize a person even if he is static. In fact, we will do that with a very high accuracy of a median of 12 centimeters, which is about half a foot. But before I describe to you how we can achieve this, let me first tell you how state-of-the-art systems in this area work. The way these systems work is by using wireless reflections. So they have a transmit antenna and a receive antenna, and they will shine a wireless signal, which will reflect off the human's body, and then it will come back. And what they want to do is they want to use this signal in order to localize the person. And the first step to do that is to compute the distance to the person. Now, to compute the distance, they use a very simple equation, which we all know, which is that the distance is equal to the speed of light multiplied by the reflection time. So if they can measure the reflection time and they know the speed of light, then we're golden, we can get the distance. So how do they measure the reflection time? Well, one approach is to transmit a very narrow pulse and measure the time it takes the pulse to reflect and then come back. But to get centimeter scale accuracy, you would need to measure time at the order of tens of picoseconds. This is extremely expensive. So instead, what these systems do is that they use a technique called FMCW that allows them to measure time by measuring frequency. Let me explain to you how this works. An FMCW signal consists of a signal whose frequency linearly increases in time. So over here, you can see that time and frequency are linearly related. Now this signal will reflect and come back after some reflection time. But I told you that this reflection time is very hard to measure. Now the really nice thing about FMCW is that the transmitted and the received signal are also shifted with respect to each other in frequency. So if you can measure this frequency shift, then you can simply divide it by the slope of the signal that you generated, and then you will get the reflection time. It turns out that it's extremely easy to measure this frequency shift. All you need to do is to use a component like the one in my hand. It's called a mixer. It's passive, low power, and in fact, it's found in all of our wireless transceivers. Even your cell phone has multiple mixers. So to summarize, what these systems do is that they use FMCW and a mixer to compute the frequency shift, map it to the reflection time by dividing it by the slope, and then they can get the distance. Now, if we know the round-trip distance from the transmitter to the person and back to the receiver, then we will know that the person is on an ellipse whose foci are the transmit and the receive antennas. Because any point on that ellipse has the same round-trip distance. To localize the person, all you need to do is to add another receive antenna intersect the ellipses, and you find the person's location. So now that I have told you how these systems are able to localize a person accurately, let us go back to their limitations. Why are these systems limited to tackle a single moving user? Well, the reason is because of how these systems deal with multipath. Dealing with multipath when there is a single moving user is extremely easy. But dealing with it when there are multiple people or when one of them is static becomes extremely hard. Let me explain this. So when you have a transmitter and a receiver and you have a person, then the signal will reflect off the person and come back. But if there's also a table in the environment, then you will get two types of multipath. First, you will get the table's direct reflection, and second, you will get an indirect reflection, that is a signal that bounces off the person then the table, or the table off the person before coming back. Now, to eliminate both of these, it's easy if you have a single moving user. To eliminate direct reflections, all you need to do is to take consecutive measurements and subtract them out from each other. Because the table remains in the same place, its reflection disappears, but because the person moves, he survives the subtraction step. Now, of course, what this means is that you need the person to move in order for you to localize him. And if a person is static, you will not be able to get his reflection. Now, eliminating indirect reflections is also easy when you have a single moving person. And all you need to realize is that the round-trip distance of the direct reflection is shorter than any round-trip distance of an indirect reflection. So you can simply choose the first person you localize and say, this is the person who I have in the environment. Now, of course, this will fail if you have multiple people, because the second person's reflection might be further away than an indirect reflection of the first person. So if we want to localize static people, or if we want to localize multiple people at the same time, we need new mechanisms to deal with multipath. So in this talk, I will first tell you how we can localize multiple people, and then I will go back to tell you how we can eliminate direct reflections. So let's go to our first question. How can we differentiate between a person and multipath? Well, our idea at a high level is that a person will appear in the same location when you view him from different vantage points, but multipath will be inconsistent. So to intuitively understand that, I want to ask you to look at me. People who are looking at me from this part of the crowd will see me here, but will get reflections from over there. But people who are looking at me from this part of the crowd will see me here, but will get multipath from behind me. So both of you guys saw me in the same location, but you observed multipath from opposite locations. And what this means is that if I combine observations from different vantage points, then the different vantage points will agree on my location and disagree on the multipath's location. So now that I explained this to you at a high level, let me show you how it works in practice. So we run an experiment with two people who are moving in fully furnished rooms, and this is the output that we get from a single vantage point. Now over here we see a heat map that shows the probability distribution of where we think the people are, and red shows highest probability, while blue shows lowest probability. And the different ellipses that we see correspond to the round-trip distances that I told you about before. Now this is the output that we get with one vantage point, and if we add another one, this is the output that we get, and if we add 16, this is the output that we get. Now we are clearly able to get the two people's locations, and we will be able to localize them. And the more vantage points we add, the higher our accuracy of localization is going to be. Great, so this gives us a way to eliminate the indirect reflections. So are we done? Well, not yet, because we still need a mechanism to find 16 different vantage points. Of course, the naive way to do that is to add one transmitter and 16 different receivers. But that would be expensive and complex. Ideally, what we want to have is 4 transmitters, 4 receivers, and have all the combinations of transmit-receive pairs, which would give us the same number of vantage points. But even more fundamentally, the second approach was only scale with the square root of the number of vantage points, while the first one will scale with the number of vantage points. So we really want to go with the second approach, but it also has a problem. And the problem is that the different transmitters will interfere with each other over the medium. So how can these different transmitters share the medium without interference? Recall that what we have is an FMCW signal where time and frequency are linearly related. and say that we want to use FDMA, or frequency division multiplexing, to share the medium. So the first transmitter will use its own frequency band, the second transmitter will use its own frequency band, and each other transmitter will use its own frequency band. What this would mean is that you would need n times the bandwidth in order for you to localize. Okay, so what about TDMA, or time division multiplexing? We will first transmit from the first antenna, then the second antenna, and so on and so forth. But then this would mean that we would need n times more time in order for us to localize. Ideally, we would want all the transmitters to be transmitting at the same time and in the same frequency band. Now, of course, we cannot have all of them transmitting at exactly the same time and in exactly the same frequency band, because they will definitely interfere. But what my claim is that we can bring them all very close to each other, let them transmit without interfering. So we're going to do something like this, and we're going to stack all of them at the same time. So let me tell you why this would work. Remember that the objective of our system is to transmit a signal and get its reflections. So when we transmit from the first antenna, we'll get a reflection that arrives after some time. Now, the really nice thing is that in indoor environments, all the reflectors are very close. So beyond 100 nanoseconds, you will stop getting any reflections. And all I need to do is to ensure that my second transmitter neither interferes with the first one or with its reflections. So I just need to delay it by an amount larger than the largest possible reflection time. So for example, over here, I can transmit the second transmitter. And any reflection coming after it will correspond to the second transmitter, and any reflection arriving before it will correspond to the first one. And I can do the same thing for the second transmitter, and so on and so forth. And what I want to note over here is that if you look at all of these transmitters, they are not using TDMA. At any point in time, they are all transmitting, and they are using the exact same frequency band. And we call this technique multi-shift FMCW, and it allows us to transmit from multiple antennas at the same time, in the same frequency band, and without interference. So to summarize, in order for us to localize multiple people, we're going to use multi-shift FMCW to transmit from multiple antennas, and then we're going to combine the different vantage points in order for us to eliminate the indirect reflections. So now that I have told you how we can eliminate indirect reflections, let us go back to the other problem. How can we accurately localize static users? Well, to see why this is hard, let us go back to the challenges that I talked about. The way we eliminated direct reflections is that we did subtraction. Because the table stays in the same place, its reflection disappears, but because the person moves, his reflection goes away. Now, of course, if a person remains static, then his reflection will also go away, and we will eliminate it by subtraction. So how can we localize static people? But then, is it true that humans are no different from inanimate objects like tables or chairs? Even if you are sitting there, you are breathing and your heart is beating. So something in you is always moving, and our hope is to be able to exploit this motion to localize static users. In fact, by exploiting breathing motion, you can even differentiate between static users and other vibrating objects in space. But again, it is not that simple. Because breathing and walking happen at completely different time scales. A person who is spacing is going to move at 1 meter per second. But when you are breathing, your chest moves only by a few millimeters per second. And so we cannot use the same subtraction window in order for us to eliminate multipath in each of these cases. So for example, let me give you an example where a person is moving at 1 meter per second. If we use a 30 millisecond subtraction window, then the person will have barely moved. By subtraction, you will find his location accurately, as you can see over here. But if we use a 3-second subtraction window, then during these 3 seconds, the person will have moved by 3 meters. Okay, after you perform subtraction, you will eliminate the static multipath, but the person will appear in 2 locations, the first location and the final location. On the other hand, if you want to localize breathing motion, then you need this larger subtraction window. Because if you use a short subtraction window, you will not be able to capture the person's location because the chest will have barely moved. But if you use a 3-second subtraction window, then you will be able to very accurately localize the person. And so our idea is that we're going to use multi-resolution subtraction windows to eliminate static multipath, and at the same time, be able to localize both moving and static users. And now that I have described to you the basic components of our system, let me show you a video of how it works in practice. In this video, we're going to start by having two users who are sitting down on chairs, and the output is shown in the bottom left corner. Now, because these users are sitting, we're going to be exploiting their breathing motion in order for us to localize them. So it will take us some time after I play the video. Now that I played the video, after 3 seconds, we are able to localize them as the blue dots on the chairs. And when a person comes in and starts walking in the environment, we are able to localize him very accurately, even though he is walking very close to these two people. And in fact, we do all of this by relying on a single device that is shining wireless signals and collecting their reflections from the environment. And now that I have told you about the components, let me tell you how we implemented and evaluated our system. To do that, we built an FMCW front end and connected it to a software radio. And I told you that the signal changes frequency, so we changed it between 5.5 and 7.2 gigahertz in a manner that complies with FCC regulations. So in order to do that, we transmit at very low power, at 70 microwatts, that is 1,000 times lower than what your typical Wi-Fi access point transmits. And we use a multi-antenna setup like the one shown over here with multiple transmitters and multiple receivers. Now, to evaluate the accuracy of our system, we use the Vicon motion capture. Vicon is used in filmmaking to track actors and map them to 3D character animation models. So it has an array of infrared cameras on the ceiling, and you put different infrared reflective markers on the person's body, and you can track them accurately with sub-centimeter accuracy as they move. So let me show you some of our results. First, let me show you our accuracy in localizing multiple people. We run 100 experiments where people are asked to walk randomly in a room, and we plot the error as a function of the different users. And these are our results. As you can see, the median accuracy is less than 15 centimeters in each of the dimensions for all of the users. In fact, even our 90th percentile accuracy is lower than 50 centimeters. To give you a comparison, this is of the same order of the accuracy that you'll get if you ask users to hold a device or wear it on their bodies. Now let me also show you the accuracy of localizing static users. We ask different users to sit in different locations in the environment, and again we plot the error as a function of the different users. And here are our results. Across all of the users, our accuracy for localization is less than 10 centimeters in the x and y dimensions. In fact, even the 90th percentile error is lower than 40 centimeters. And if you're wondering how come we can localize static users, even with a better accuracy than moving users, keep in mind that we're using longer windows. So we have more measurements in order to find their location. And our research built on past work in many related areas. But it advances this to enable accurate localization of multiple users and of static users at the same time. To do that, I have told you that we have exploited properties of indoor multipath, such as its structure when you observe it from different vantage points, and the fact that all of this multipath is very close to you, and so you can do some form of spectrum reuse. And I have also told you how you can localize both moving and static users and eliminate multipath using a multi-resolution subtraction window. But of course, this work has limitations. It cannot know who the person is that it is localizing. For example, it cannot know if the person is me versus my colleague Zach versus my advisor Dina. And also, our current implementation is limited to tracking 5 users because of the compact setup and the number of vantage points. But I want to remind you that this is a very nascent research area. We are only starting to understand what we can do using wireless reflections. And as our understanding will evolve, so will the applications and the capabilities that we can achieve. So for example, I have showed you that we can get a person's location from his breathing. And now I want to show you that we can do even more than that. And to do this, my colleague Zach now is going to sit down. And I'm going to be using these antennas that are over here in order for me to track his breathing. And first, I need to switch. Okay. Now I am going to run this. Okay. Now let me show this to you. And I need more force to do this. Okay. So over here, he moved a bit at the beginning, so we are unable to get his. We were unable to get his breathing, but once the window shrinks again, we will be able to see that we are able to capture his breathing. Sorry, this is going to take some time because of the window. Okay. So the large increases and decreases in the signal are actually due to his breathing. We can now see his inhale and exhale. And now I want to ask Zach to hold his breath. As you can see, when he holds his breath, we stop seeing these large variations. But we still see some minor variations. And these are actually due to his heartbeats. Zach, please release your breath. We want this to stay alive. And once he releases his breath, we are able to get this increase and decrease again. But this is not all we can do. What I'm showing you now is Zach's heart rate. His heart rate is around 70 beats per minute. And these changes are perfectly normal for him when he is sitting there. In fact, I'm not going to show you my heart rate. He's very close to me because I'm clearly nervous. But with this, I will wrap up my talk and take any questions. Thank you.
Yeah, I was wondering here, aside from localization, have you thought about using this technology to do life safety monitoring, like whether somebody is injured or in distress or something like that from breathing their heart?
This is an amazing question. Actually, we are talking to the fire department in Boston to try to give it to them. I mean, they don't have a lot of funding, so it takes a lot of time to implement this. But yeah, this is one of the very exciting applications. There's also many exciting applications in other domains. There's the healthcare domain, baby monitoring. Imagine if you can get the breathing and heart rate and put it into your baby monitor, you can start tracking people's. You can just look at your phone and you say, oh, okay, my baby is breathing. He's perfectly fine.
Hi, Rick Farrow. So how many antennas do you have in the device that's sitting on the table?
So in the current device, I have only 2 antennas. And the reason is I was not getting, I did not care about getting the 2D location. You need more antennas to get the location, but you need only 2 antennas in order if you want. Actually, you need only 1 antenna to get the person's breathing and heart rate, and even separate me from him and everyone else here.
So 1 transmitter, 1 receiver.
Or a full duplex DSLR exchange.
Yeah. Okay. Hey, thanks.
Thank you.
Yeah. So if you want to track lots of people, let's say, how does your system scale? Let's say with number of people you want to track, and also it's more challenging if you do it outdoors. Yeah.
To do it what?
In outdoor environment rather than an indoor environment.
Okay. 2 questions. One is it more challenging to track multiple people? Yes. If you want to track multiple people, you will have to add more vantage points, or you need to place your vantage points multiple devices and then combine across these multiple devices. In this experiment the experiments that I showed you, all the people were moving in a small area, and we had a single device that was placed on one side of the area. Now, in outdoors, you could use this outdoors, but you could also use GPS. So that's why we were focusing on indoors. But I would imagine that it would work better outdoors because you have less multipath.
Could you comment on the performance of your systems in case of intrinsic motion in the environment, like a fan rotating in the room, or if I leave my window open and suddenly wind blows in and moves the curtain?
Excellent question. So I told you that we can get the person's breathing and heart rate, and actually we presented this work, the breathing and heart rate, last week at CHI. And the idea is that you can isolate the different sources of movement. Once you isolate the different sources of movement, you can detect if the movement is, if something is remaining in the same place, you can see these periodic movements. And a person's breathing and heart rate are always in a predefined band. So you can use them in order for you to distinguish between a human and other fans or objects in the environment. For example, if you look at a fan, yeah, it is moving, but a breathing motion happens at 10 seconds, whereas a fan would rotate like once per second. So you'd be able to easily distinguish between the two. You have questions? No? You have questions for me? I don't. Okay. Thank you very much.